In our third mechanism here, we are turning a ketone into a final product, which is an acetal. And both of these oxygens in this acetal are coming from the oxygens on the alcohol molecules that are adding. So we're adding a alcohol molecule twice and then getting rid of the original oxygen here as water leaving. So overall, we're going to break the sigma and pi bond to oxygen, and we're going to form two OH bonds here. And so this is going to become water. So we're forming two OH bonds and breaking two CO bonds. So down here at the bottom, forming two OH bonds and breaking two CO bonds. And then when our alcohols are coming in, each time an alcohol comes in, we're going to form a new CO bond. So we're forming each of these two new CO bonds, and we are losing a hydrogen off of each of these oxygens. So we're breaking two OH bonds and forming two CO bonds in the end there. So a total of 4 bonds broken, 4 bonds formed. Let's see what we can do here. So let's start out by looking at the reactivity of the species that are involved. We have a moderate electrophile, as we have identified it as before. Ketones and electrophiles, or ketones and aldehydes are moderate electrophiles, and then we have this thing which is going to act as a nucleophile, but it's as good a nucleophile as water is. It has no negative charge on it at all. It's a neutral oxygen, and so this is actually a poor nucleophile. So in the last mechanism we looked at with a nitrogen nucleophile, the nitrogen nucleophile was a moderate nucleophile, and we could get away with that reacting with the moderate electrophile. But now we have a poor nucleophile, and it will not react with the moderate electrophile. You dump these two things in together and wait 10 years and check on them, and not much has gone on at all. So that's why we need the acid catalyst in here. So the acid catalyst is going to convert this moderate electrophile into a good electrophile. So one of the things that we're going to have to do in this overall mechanism is to add 2 protons onto this oxygen to make it leave as water before, as we're bringing alcohols in. So let's add a proton on there to begin with and make it into a protonated ketone, and that protonated ketone, which has complete octets and has a positive charge on oxygen, has another resonance structure which is just about as good as it is. It has an incomplete octet on carbon, but it has the positive charge on the more electropositive carbon. And so what we have here is 2 resonance structures, one of them that is putting a positive charge on this carbon. And you can make an argument for this has complete octets, so maybe it's a little bit more important than this one with incomplete octets, but then the positive charge on the more electropositive element makes this better in one sense than having the positive charge on the electronegative element. Either way, we can make something up, and we can say it's maybe a little bit, this is maybe a little bit more important resonance structure, so this is 55% and this is 45%. But the point is, there's almost, by this resonance, there's almost a half of a positive charge on that carbon. And you might argue that there was a positive charge, a little bit of a positive charge on the carbon to begin with. You could draw resonance structures of this. But this resonance structure is no comparison to the one that we have drawn here. Okay, complete octets, no formal charge, incomplete octet, and 2 formal charges. So this isn't particularly important, and we can make something up. We can say that this is 97% and this is 3% or something like that. But this is not a very important contributor to the overall resonance hybrid. But once we had a proton on here, then we have turned this moderate electrophile into a really good electrophile. And again, the reason is that we now have almost a full, or almost a half of a positive charge here on this carbon. And so we can add that to our list down here of the steps, and we can keep track of the bonds that we've broken. So what have we done in step number 1? What is that called? That's our protonation. So step number 1, protonation. And we have formed one of the OH bonds that we need to form. So we can check off one of the OH bonds that we have formed there. So now we have our positively charged good electrophile and our poor nucleophile, but it's good enough nucleophile to attack our much better electrophile than we had before. So we're adding that on to the positively charged carbon there. And we could have drawn this curved arrow over here, or if we drew it over here to this resonance structure, it would have been a little bit more obvious what type of reaction is happening here, because as we're attacking here, we're breaking the pi bond. So if we're breaking the pi bond, what kind of reaction is it? Put that down here in your second step. Breaking pi bond. So we did an addition there. And in the addition, we formed a new CO bond. And so we can go down here and check off that we formed a new CO bond. Okay, so we have added one of the alcohols that we want to add, but we really wanted to, and the whole thing has a positive charge, and we really wanted to just add the OR, and we're not interested in the hydrogen, and so we can, it's in acidic solution, so we can lose the proton into solution, deprotonation. And we could have shown an alcohol molecule pulling it off, or we could just show it going off into solution. But minus H plus deprotonation, so we are breaking an OH bond, and we're doing a deprotonation. Why did we do that in this step? I mean, why did we choose to do that? Well, it had a net positive charge, and if we did another protonation on it, because we want to protonate this and make this a good leaving group, then we would have had 2 positive charges on the same intermediate, and that's not possible. It's too high energy. So before we can put a proton on here and make this a good leaving group, we have to take this first proton off. And look at this sequence of reactions. Protonation, you do something, you deprotonate. You deprotonate. Okay? So again, common sequence of events. Next thing we want to do here is to get rid of this OH to give room for another alcohol molecule to come in. And we can't just kick out the OH. If we do, then we're creating OH minus a strong base in the middle of an acidic solution. And so that doesn't make any sense. We can't generate strong base in acidic solution. So what we need to do first to make it a good leaving group is to protonate it. So the next step is protonation, creating this intermediate. Now we have a good leaving group, and we can list that as protonation and check off that we formed another one of the OH bonds that we are wanting to form in the reaction. And then we'll pick up on the next video. Now that we made this a good leaving group, let's go ahead and kick that out in the next step. In the next step.